So the counts in the three levels, two levels, is the multinomial.
Okay.
The counts in the binomial is the what? In the Bernoulli, the count is the binomial. Okay. And then those, so in the multinomial, we also have the what? The Bernoulli, right? Because we have to count the Bernoullis for all the three levels, right? Yeah, so so that becomes
So
yes.
I'm a bit confused. We're saying the trial, on the count of the trials for binomial, the Bernoulli. And the count of the trials for binomial, Bernoulli is the binomial. So we are looking at the yes or no as the Bernoulli trial.
Yeah.
So the more than two trials or the multiple count, the name is multinomial. So what do you call the individual elements?
So the individual will still be.
So I'm saying that binomial is multi, what do you call it?
So binomial.
As Bernoulli is what?
Okay, so let me explain it. So Bernoulli is to binomial for two levels, and then Bernoulli to multinomial for more than two
So
levels.
in both cases, it's no Bernoulli. That's what I want to understand.
So in both,
Okay, is it the terminology is talking about
yeah, so the Bernoulli like the start, right? Yeah, so because it's yes or no, if I have three options and then you choose one, if you have a choice to either choose that one or not choose that one, right? So for each of the level, I have the choice, should I choose you or not choose? So you have like,
Okay, so it's not as if the Bernoulli is limited when you have two options.
so the option, so the if it is two options, then it is what binomial. Okay, and if it is more. So like religion, right? So I think I should have like I have an accident, and then I ask, is the person injured or dead? Or not choose it. Okay. And then choose this or not choose this. For polynomial is it's in the regression. Like if you have a straight line, you know a straight line is ax plus bx, a plus bx. You have an intercept and a slope, but the x, if you now increase the maybe x squared, s cubed, then you are in a problem. So it's something different. Okay, so I have a very simple example of how useful they are. If I know them, so for example, so let me just go through this example. So assuming that I have 10 multiple choice questions and with 5 possible answers for each, okay? What is the probability that a student who is unprepared and therefore made random guesses for each question will make 0 correct responses? Will make 1 correct response? You will not know, right?
Yeah.
But if you assume you know what the population is, then you'll be able to answer that question. Okay, so I'll not go through this example is because it's just when you have time, just go through it because of our time. Okay, so the distributions are good, right? So we have the Bernoulli binomial, and then okay. Now, when we specify, when we say that we know the distribution, okay, when I say we have made an assumption about the distribution, okay, then it means that every distribution is characterized by a parameter. It's something, so we don't know everything about the distribution, but we have information that when I know that information, then I know that's distribution. Okay, so for example, if I say a Bernoulli, the parameter of interest is the probability of the sources. Okay, so if I know the probability of the sources, then I know the distribution. I can describe everything. Okay, so probability of sources, then it means that I know the distribution. For the binomial, it is the same. I need to know what the probability of the sources. So the probability of the sources is the parameter that we need to know to say that we know the distribution of this population. That's it. So we have distribution and then the parameters that define the distribution. For the binomial, the probability, the parameter is what? Bernoulli. The parameter is for Bernoulli, the parameter is the probability. That is the proportion. So if you are doing a study, you are interested in knowing the what? The prevalence of a particular condition. Okay. So the prevalence of that particular condition is your parameter of interest. Okay. Then if it is also binomial, it's the same thing. Okay. And then if it is multinomial, it's the same probability, but probabilities for each class. So what is the probability for, if it is binary, you highlight one. So the probability of the sources. Okay. If there are 3 categories, then it is the probability of each of the categories. Okay. So we use probabilities to describe what? Our distribution. So that means that anytime we say we know something about the distribution, then we are saying that we want to know something about what? That parameter, which is the probability. Is that clear? Okay. So the probability is pretty sensitive. So forget about probability. Think about it in terms of proportions. Okay. So we want to know the what? The proportion. So the parameter is the proportion. So if the parameter is general because it depends on the distribution, then the parameter of interest will be different. Okay. So it means that the proportion is what we are interested in. So if I collect data, binary yes or no, then my interest is to know what? The proportion of people who are what? Sources. Exactly. So how do I estimate it? So the estimation, how do we know the probability of sources? For that parameter, we just calculate the what? The proportion. Okay. So if I have a data and then I want to, I have binary yes or no. What is of interest is the what? Is the proportion, right? The proportion of what? Sources, which I can calculate from my data. Okay. Yes.
You see that the proportion of the failure will be more than the proportion of the success.
Yeah.
So in that case, I think
so that's why it will depend on. So like I said, there is no rule of which one should be there. So that's why I say you have to highlight the one that you want. So if I decide to I want to highlight the sources, then that is the one that I will
if I highlight the sources, I realize that if conducting my I realize the failures are more than the success. Do I still go?
It doesn't matter if they are fewer. That is what you are doing the research for. You want to be able to say that that proportion is what smaller in that area. So it's a scientific question of interest. So if I want to know the prevalence of a particular condition, anemia, right? Prevalence of anemia, and then I say that it's too small. So I want to report the prevalence of non-anemia. So it depends on It's very small. Okay, and then you can transcribe. Okay, so we know we want to estimate the population quantity, which is the proportions. All right. So somebody must make a claim, and then you want to verify. So now we are now moving into data analysis and why we do data analysis. Okay. We have a quantity that we are interested in. In our case, it is what? Proportion. In other courses, it will be the mean. All right. But for categorical data, it is the what? Proportion. So somebody comes, and the proportion is what? The proportion is, so the proportion is what we want to know about the population. We've not gotten there yet. So for now, we want to estimate a population quantity. All right. So we are still at the population quantity. So the population quantity is we want to know the prevalence of a particular condition. Okay. So that means that there is a prevalence that is associated with the what? The population. And then when we go and we collect the sample, then there will be a what? Prevalence that is associated with the sample that we have collected. Because it will not be the same as the population. Okay. But obviously we don't know what is in the population. So we make hypotheses. All right, we do a guess. So an expert comes and he says, I think in Ghana, the prevalence of malaria is 12%. Right? In Ghana, the prevalence of malaria is 12%. So whatever we have said about the prevalence of malaria is the what? Population. So the person is assuming that in the population, the prevalence is what? 12%. Then you as a researcher, you are not sure. So you say, no, I have to verify it. Okay. So the claim that somebody makes becomes the hypothesis that you want to test. Okay. So if you have any claim, then that becomes your what? Your hypothesis. So we call it the null hypothesis. Okay. So for in this case, the null hypothesis, we always write it as what? H naught. Okay, H naught means that the null hypothesis. And the alternative hypothesis is the counterclaim. No, the counterclaim. Now we have not even gone to the field yet. Somebody have just come with a claim. You are still, exploring. I'm saying that the prevalence of malaria, malaria is 12%. Okay, so that is a claim that I have made. Then you think that no, it cannot be what? 12%. So you make a counterclaim. All right, you have not gone to the field yet. You have not gone to the field, but you make a counterclaim. No, it is different from what? 12%. So if you make that counterclaim, then you must go to the field, collect data, and verify. Okay. So anytime, all the time, we always state the null hypothesis and then the what? The counterclaim, the alternative hypothesis. So we'll collect data to test this. Okay, so in the population, the prevalence is 12%. The counterclaim is that no, it's different from what I.
And you are not different from the but you also having not to the
yes, so that is why you have to now. So it means that when you are making your counterclaim, then you are prepared to go to the field, right? Okay, so we'll now go to the field and then we collect data. So why are we going to the field to collect data? We are going there to gather what? Evidence. Okay, for that claim, to support the claim that the person has made. So I go to the field and then I'll collect what? A sample. Is that clear? So I go and I collect the sample. So when I collect the sample, I compute the prevalence from that sample. Okay, I collect the prevalence. I calculate the prevalence from that because I sampled, I test them, do you have diarrhea, yes or no? And so I'm able to get what? A quantity that represents the sample what? Prevalence. Okay. Now the problem with that is that it's possible that it is your sample that has given you, maybe you got 12.5% when you went to collect the data, right? But the person can still challenge you and say that no, that 12.5%, maybe you did some selection and then you got so that you'll be able to get something closer to. So the problem is that you can, when you go to the population several times, you get what? Different results. Okay. So whatever results that you have obtained is not, you cannot conclude that, because I also went to the field and then I collected my sample and then I got 12%. It means that the person's claim is true. Okay. So what I need to add is that in the population where I'm studying, what information do I know about the possible sample? So if somebody should also go there, how would the results change? Okay, we call that the variability. Okay, the variability. So that proportion that you can always change. What is that variability? Okay, so the variability is another information that because we know the distribution that we have imposed, we know once you give me the prevalence, I'll be able to calculate the variability. And then I'll use that to perform a test. Okay? So I'll use that to perform a test. And then when I conduct the test, then I'll now be able to say, look at the p-value of that test. So if my p-value, okay, so there's an inference that will come. Okay. Yes.
If the person says, let's use your example as 4%.
Yeah.
And I use the alternative hypothesis, can you set it below the 12% or above or going to the test? Or if it is below, you can only say that person is.
Right. So that's what I'm saying, that we don't know. It's possible that it can be higher or it can be lower. Okay, so there are so many possibilities. But if we are able to know how they possibly can change, we cannot tell unless we go to the field so many times. But because we have pretended that we are God and we know the distribution, we are able to calculate that variability. So we can make use of that information to now conduct a test. So we'll now compare whatever we got with whatever the person's claim was. Okay, so whatever we got, we subtract whatever the person claimed. The person says 12%, right? And then we said it's what? Maybe when we collected the data, it was let's say 14. So I'll take the difference, and the difference is what? 2. The question is that 2, is it significant or it's not significant, right? But I cannot say that unless I know how they are varying, because the variability is very important. I have to know how they are varying before I can make that. So the problem is that we want to know whether that 2 is true or not. Okay.
If it is true, whether it's
Or not. Yes, precisely. Okay, so what we have here is that, so we have the null hypothesis. It can be true. The person's claim can be what? True or false, right? And then we can also reject the person's claim, or we can what? Accept the person's claim. Okay? So that means that it's possible that the null hypothesis can be true. So that's like the truth, right? It's possible that it is true that the null hypothesis, the person's claim is true. It can also be true that the person's claim is what? False, but we don't know. We are conducting the test. We can reject or accept the person's decision. Okay? So if indeed the null hypothesis is true, and then we accept it, then we have made what? A correct decision. Okay? Then we have made what? A correct decision. However, if the person's claim is false, and then we accept it, then we are making what? We are making what? An incorrect decision. Okay, that incorrect, the probability of us making that incorrect decision where we reject, okay, so where we accept the null hypothesis when it is false is called a type 2 error. Okay, so the other one is called what? A type 2 error. The person's claim is what? False, but then we have what? Accepted it. So that is a false claim. It's also possible that the null hypothesis is indeed true, but we have what? Rejected it. The null hypothesis is what? True, and we have rejected. So that is another error. We call that what? The type 1 error. And then the null hypothesis is false, and then we have what? The null hypothesis is false, and then we have rejected it, right? So it is false, and then we have correctly what? Rejected it. So that's the correct decision. So now there are two types of errors. The probability of committing a type 1 error, which we denote by alpha, and then the probability of committing a type 2 error is denoted by what? Beta. Now the probability of committing a type 1 error is the what we hear as the alpha level or the significance level. Okay, the significance level. All right. That significance level is the one we always specify as 0.05. Okay, so when you are conducting a study, you want to reduce this type of error, the type 1 error rate.
So type 1 is the claim is false. You accept it.
The claim is true, and you have rejected it.
True but rejected.
True but rejected. That's the type 1 error. It is the, okay, so if someone is guilty, all right, somebody has committed a murder, and then someone has not committed a murder. Yes. And then a decision has been, and he's sent to court. Okay, so you have not committed a crime, but then you have been sent to court, and then you are jailed. And then someone who commits a murder is released.
Yeah.
Which of these is more serious? The first one. The first one is more serious, right? Okay. So, and that is the type 1 error. So even though we have two types of error that we have to control, we have to always make sure that we limit the what? The type 1 error rate. Okay, because it's like more. Because if the person is a criminal and then he's released, it's okay, allow him to go. Because he's a criminal, he will commit that crime again and finally he'll be caught. Okay, rather than sending an innocent person to court, and then, I mean, you'll be there for many years. Okay, and that is very bad. So in statistics, we always want to what? Reduce that type 1 error rate. Okay, so the type 1 error, so every researcher, once you are beginning your research, you have to, and this error rate, you can't do anything about it. It becomes your choice. You have to make a choice that in this particular study, I want my type 1 error rate to be what? 0.05. Okay, so this 0.05 you get, it's not just, most research fields use that 0.05, and there's a reason for that. So like, but in some like medical studies, okay, then they use 0.1 because then, I mean, if you make small mistakes, you can lose, some people will die. Yeah, so some trials use the 1% error rate. Okay. So we know the type 1 error rate. We always must what? Specify it. If it is 0.5, we know that it's what? 0.5, right? Then we go to the field, we collect our data, and then based on the evidence that we have, yes. Yeah, so I was saying that some people take the error rate to be, so it's related to what we call confidence. All right. So if I say I want to make an error of 0.05, then it means that I am 95% confident that whatever result that I get is true, right? So that's the 95%. So the 95%, you just subtract 1 from it, so you get there. And then so that 95% depends on the goal. Some people want very high precision. They want like 99% sure. So then they will, by some social science research, they can even go as being 80% confident. That means, and that's like 1 error rate is what? 0. Yeah. Okay, so so I mentioned that there is because I this ones will take a lot of time, but I want to skip it and talk about the p-value. Okay, so the p-value, yes.
Is the H not always based on an assumption, or you can make an H based on a statistical? Can you make I mean the now hypothesis, is it always an assumption, or I can make out of something novel, I can take data, analyze, and come up with a now hypothesis?
Okay,
Is it
so
always an assumption?
not always an assumption. So somebody can be doing a study. The problem with statistics is that even though we are always interested in the population quantity, it is the reason why we are conducting our research. The problem is that because we don't know the truth, we have to make that assumption. So when we make that assumption, then we are assuming that that is the truth, that we know the world now. As long as that assumption is true, then that means that now we have control. So that information can be based on an expert. Maybe somebody is working in that field. He has been seeing patients so many times. So he can be able to tell you that, no, roughly, I know about this number percentage of people who have this condition, right? So it becomes like this. It could also be that somebody has done a similar study or a research where
No assumption as the previous.
no, all of them. He also might have done some assumptions, okay, and then, but then maybe because he has actually gone to the field to collect data, you say that, okay, based on this the data that he got, now I want to use the value that he got from his study as my truth. Okay, so that you can use that. So that's why you have to do a lot of research. Sometimes it's also possible that the settings are different. So maybe the proportion that you are reading from there was a study that was conducted in an urban area, right? You cannot use that proportion when you are conducting your study in probably an urban slum area. So even though it's also urban, but it's a slum community, your study is going to be conducted on, right? So when you take that value and you just plug it in there, you know that there will be a cost. So it can be based on an expert's advice, or you can also rely on literature work, or you can be based on, if I'm testing a new drug that nobody has used before, then you can, based on your own intuition, experience or intuition, you can also specify this value. Yes, it must be. Realistic. If not, it has implications on
Who determines the realistic?
who determines the.
It's Christian.
Yeah, so the thing is that once you do that and you collect your data, you are able to go back and check whether the assumptions that you made were correct or not. Okay, so you can always like, so when the person now does a study and he reports the truth, you can use the value that he has used to re-engineer and see whether the sample size that you collected were enough.
So, if understood myself very well, what he's trying to find out is that it's always assumption or you know.
It's a claim.
It's a claim.
Yeah, it's always a claim that's the reason why you are doing the research. Yeah, it's always be, if you know it, then why would you do the study in the first place, right? So you must make a claim and then try to see whether you can validate that claim or not. Okay, so that's the whole idea. Okay. So I have the alpha, the type 1 error rate, which is the 0.05. Okay. Then when I do my study, so that the p-value would depend. I wanted to explain the p-value, but it will take us some time. But let's use the p-value as like the type 1 error rates that we have computed based on our whatever we have observed, right? And we use it to benchmark the cutoff that we have imposed, that we want to make sure that our type 1 error rate is what? 0.05. Okay. Then the p-value is trying to quantify what is the probability that we have observed something more extreme than what the person's claim was. Okay. What is the probability that when we collected our data, we observed something that is what? More extreme than what the person has said under the null hypothesis, right? So we want to see how far away we are from that person. So if we quantify that and then we see that, oh, we are maybe say that if the event is very real, and then the probability that you are even more extreme than that is smaller than my error rate, then the person's claim cannot be. Right? So the inference person will come and then maybe he will take his time and then go through it step by step. But because we need it to do the kind of things. Okay. So somebody makes a claim, right? Somebody makes a claim. I've collected data and then I have what? Done my analysis. Now the person of the person's claim. Okay. Okay. So if the probability that I am more extreme than that person, I mean, it's an event that is not, it's real. Like it's so much extreme is very real. If something that is so extreme has happened, then there's a question, right? A question mark to it. If the thing is so, if there's something that is unlikely to happen, if it happens, what would be your judgment? The thing is so unlikely to happen, and then it has happened. It's strange, right? So that means that the person's claim might not be true. Is it the same thing?
Yeah.
Okay, so let's say it many times, maybe you get it. So I have computed the probability. What is the chance that whatever I have observed is more extreme than, so more extreme is that it's very, very far away from, if I will get a value, if the person's claim is true, then whatever that I'll get should be very close to what of that person or very exact with that person, right? Then so I quantify it. So that means that that probability should be very high. It should be very high that if the person's claim is true, then the probability that whatever I have observed should be very high. That this assertion is what? True. But the probability that I have got is very small. So the probability that is very small. That means that the evidence that I have is saying that I am what? Really very far away from that person's truth. Okay, so then his claim cannot be true. Yes.
Now will come to play. We'll see that extreme outcome.
Yeah.
I think after that time. For example, maybe the time of taking the sample. Maybe you like also.
So that is a good point. That's what I mentioned, that it's very possible that when you go and collect the data once, okay, maybe you didn't collect your data very well. So if you are getting something that is different from that person, then the person will question you that, hey, maybe it is your sampling procedure. Okay, but when you do the statistical analysis by taking into account the variability, okay? So the variability is like you have now explored all the various possibilities to come up with that conclusion. Okay, to come up with that conclusion that no, the person's your whatever you have observed is more extreme than that person's value. Okay, and that is the p-value. Okay, so anytime you think about it, so what is so you ask yourself, oh, I have collected some data. This is my data. This is the person's claim. What is the probability that whatever I have observed is very far away from what the person's claim is, right? If the person's claim was true, then I shouldn't be what? Very far away from that person, right? So it means that my probability of going very far away from that person will be very high, right? Will be very small. Okay, will be very small. So if something that is very small happens, then it means that the person's claim is likely not true. Okay. So we will always, even if you don't understand, just remember that I have my alpha level, which tells me how far extreme can I go. That is the error, 0.05. If you exceed that probability, that means that it's high, it's very likely to happen. Okay, but if it is very small, then it means that it is less likely to happen. So if it is less likely to happen, then the person's claim cannot be true. Okay, so we'll always be looking at what? That p-value, and then we'll always compare it with what? The alpha level. Exactly. Okay, so now let's go to SPSS and just do a simple demo. Yes. So it's like it's a probability value. So it's a probability of observing something more extreme than what you expected under the null hypothesis. So whatever the person's claim is what you put at the null hypothesis, right? So what is the probability that you observe something more extreme? Remember, the type 1 error rate is also the probability of what? Rejecting something when it is what? When it is true. Okay. All right. So let's look at this example and see how we can hear.
Is there a limit to how far can go to accept or to reject? For instance, we measure of 0.2. When you agree or agree, you have 0.2. The accepted one is 0.05.
Yeah.
But we see that we get 0.4 or whatever. There is a single.
It will depend on your research. If your research is in a very sensitive area, yeah, mostly I think 80 and above is well accepted. Okay.
So,
So,
sir, I'm confused.
yeah,
0.5 and 0.1.
0.05. 0.05.
Okay, 0.05.
Yeah.
0.0.
No. 20% is 80% is 0.2. And then the 95% is 0.05. Yeah. So the 0.05.
You have 0.01.
Yeah, you can also have 0.01, which is 99%. Yeah. So that one means that you are more confident. But you see, the more, if you are also more confident, there's implication. If you want to be more confident, so let's say I have a population of 100 people, right?
Some bros, let me ask you.
If I have a population of 100 people, and then I say that I want to be more confident, right? When can I be 100% confident? If I pick all the 100 people, right? Okay, so if I want to be more confident, it means that I have to collect what? More samples. So it has come with what? Cost. Okay, so whatever decision that you are, that's why most people will just stay at what? The 95%, that is the 0.05, so that they can, you can do the 99, but it has implications because you want to be more confident, meaning that you want to see small error. Okay, if you want to see small error or no error, then you sample what? All the 100 people. Okay. All right, let's see how, so suppose MPs cannot decide how to vote a constitutional amendment. The House decides to request a survey. If the proportion of registered voters supports the amendments exceed 0.6, the House would vote for it. So they want to decide on a vote. Test the hypothesis that the MPs will indeed vote for it. If based on a sample of 750 opinion polls, we find that 495 voters support the amendment. Okay, so you support the amendment, yes or no? If people support the amendment, then they will go ahead and vote. Okay, so now, if only 60% agrees to the amendment, then they will go ahead and vote, right? Otherwise, they will not vote, right? So what is the null hypothesis here? So we want to know whether the MPs will support the amendment or not, right? And then there is also, we have to decide whether if they support the amendment, then what is the cutoff, right? The cutoff is what? 0.6, which is 60%. So if 60% of them agrees, then we would go ahead and then vote. Now this 60% could be by chance. It's just, it's just possible that you are only taking a sample of all MPs. If you go and pick all one party members, and then you ask them whether they support an amendment or not, the ruling party will obviously be what? Very biased. And so they will say, no, we don't want any amendments because we are enjoying whatever we are enjoying. Okay, so we want to make sure that we take a random sample, which is, the assumption is that we want to take a sample that is representative. So we want to see how we can do this in SPSS. So here, it's easy to compute the proportion, right? What is the sample? 750. And then what is the number who voted to support it? 495. So what is the proportion? Somebody can easily do that, right? 495 divided by 495 divided by what? 750. And what is this value? 0.66. And then, so would they vote or they will not vote? Why? So this is more than 0.6. But we all know that we are statisticians now, right? This proportion could just be due to chance. Sure. Okay. Are you sure that if we go back to the same MP population and selected this number of people, the 750 of them, they will also approve 495 would be the ones. So we have to what? Test whether this assumption is likely or not likely. Is it extreme or it's not extreme? So I'm going to switch to SP. So I'll use SPSS for this demo. Okay. So I have done the hand calculation, but let's do it with SPSS. So it's a very simple procedure we are going to use. So I hope you can see I've shown. So we have the supports, whether they support the amendment or not. Okay. We have yes and then what? No. So we just specify yes and no. And then we count how many people will say yes. 495. And then how many people says no? 255. Right? And then we run the analysis. So we can switch to our SPSS. You all have it, right? So let's all do it together. So I'm going to launch mine so that we all follow from here. Okay, so let me share this. So the online people, can you see my SPSS showing?
Yes, Doc.
Yes, we can.
Okay. All right. So before we begin entering the data, we have to go to the variable view, right? And define our variables. Okay. So the first thing we type is the name of the variable. How do we call it? Support, right? So we just type the support. And then the support was what type of response? Yes and no, right? So we can just select a string. We can just say that it's what? A string, yes and no. Can you see? Okay, so we select yes or no. The other options are not very necessary here, so I will just leave it as that. And then the second part was what? The count, the frequency. So how many people said yes and how many people said what? No. So let's let me call it count. The count, is it numeric? Okay. And then the decimal place, we can make the decimal place 0 because they are just numbers. So no decimal place. Okay. Are we good? Okay. And then we go to data view. Now we've entered the variables. We can just, the labels and other things are not important for this simple exercise. Okay. So we just go to the what? The data view. All right. Are we in data view together? Okay. So the data view, the support, we had what? Yes. And then what? No. So what was the yes? The yes was 495. Okay, 495. 495. And then the no's. So the no's will be the difference between the 495 and the So that is 255. Is it 255? Okay, 255. Okay, so this is the data that we have. So under normal circumstances, if we did a questionnaire and then we went to the MPs, okay, then each of them would have provided their own responses, right? So because this individual is an MP, he takes yes, no. This person is an MP, he takes yes, no, like that, right? So under normal circumstances, our data should have been like this. We have our MPs, 1, 2, up to what? 750 of them. Okay. And then we ask of their response. And their response would be, some will say yes, no, yes, no, no, no. So at the end of the day, the number of yeses will be what? 495. And then their noses will be 255. So this is how I should have had the data. So I just have one variable with the 2 levels, and then there will be what? This number for yeses and this number for no's. Okay. But the data has already been what? Aggregated for us. Okay. So we have to tell SPSS that no, even though the data is aggregated, they are individual data. Okay. So we have to tell SPSS that no, so that these Y's are actually going to be what? 495 of them. And then this N is what? The no's are 255. Okay, so how do we do that? So without us typing everything all over for all the all the 750, we are just going to go to our data view. Okay.
Hello.
Data view. Yes.
Please, where did you get the numbers that you inputted from?
Okay, so the data is coming from the slides. So the data is from our question here. Okay, so we have 750 MPs. Can you see my screen?
No, I didn't see the data.
But can you see my screen?
I can see the data view, but where the figure is picked from.
Okay, so it's we got it from the slides. But I don't know, can you see my slide? I'm showing my slide now. Can you see it?
Yeah, I'm seeing your data view of the SPSS, but
okay, but not the slide.
No.
Okay, so it means that I must.
You have to raise it.
Okay,
okay.
How do I share the entire
and
slide?
The data.
The slides you started
The slides, yeah.
presenting.
Let me see how to share the entire screen. Okay, let me share my entire screen. Okay, can you see my slides now?
Okay, yes.
Okay, so the number of samples were 750, and then 495 voted yes. So that is the first part. So the 495 is those who voted yes. So we are able to tell those who say no. So the no's are the 255.
Oh, okay.
Okay, so that is how we have entered the data.
Okay.
Now, can you see my data view?
Yes, please.
Okay, so now we are going to go to data view, the data menu, and then select weigh cases. Okay, so the weigh cases is now what is trying to do what we have said here. Okay, so that is the last option, and when you click on the weight. Are we there? So we can click that, and then we see that the count shows on the left side, and then we can select the this button, weight cases by. Okay, so the weight cases by, we click on the count and move it to the frequency variable. Okay, has it moved? Okay, so once that is done, we just say what? before I say that, look at here. Have you seen here? Unicorn what? On. Have you seen this on the bottom of your unicorn on? Here. See at the bottom. Can you see my cursor? Follow my cursor. Have you seen here? Unicorn on. Okay. All right. Now, the moment we say okay, we can close this box. I don't want this. Now, you see that just by it, we have now what? Wait on. Yeah, so just do the okay now, and then you see that the wait on would show there. Okay, so that means that our data has now been wait. Now SPSS understands it as coming in like this. So we have yeses are 495 and the noses are 255. Okay. All right. So now we want to do our analysis. That number that we got 0.66, is it what is the probability that we would have observed something more extreme than the 0.6 that they specified, right? Okay, so we want to get the p-value. So we now begin by analyzing the data. So we go to analyze. Are we in analyze? Okay, and then we look for non-parametric tests. Have you seen the non-parametric test? Okay, then one sample. So here we have only one what sample is just the count of the votes, yes and no's. So we can select the one sample, some observation can just say scan data and just proceed. Are we all here? Okay. Okay. Then we use custom analysis. So I've indicated the path that you follow in the slides. So even if you forget this, you can always follow from this. So we have customized analysis, right? Then we move to so that is the objective part. Then we move to the fields. Okay, so are we at the fields? Okay. So the fields, it has already selected the whatever we want to test. We want to test the yeses and the no's, right? So that is okay. It has put the support in the test field, and then we can go to the settings. The last option is the what settings. So under settings, we select custom tests. The field, just leave it as it is, okay? And then the custom test, you select the custom test option, and then select compare observed binary probability to hypothesize binomial test. Are you on the same page with me? Okay. Yeah. So have you all selected this? Yeah. Then you see that there are what? There is an option here. Okay, so we select that option, and that is where we specify the hypothesized proportion. What was that proportion? 0.6. So we just click on the top arrow until we get to 0.6. Okay. Then remember, I said if you have a binary data, there must be something that you have to highlight, right? if you have a binary data, it's either you highlight the yeses or the what? The no. Okay, here, what are we highlighting? Is the yes, right? Whether they will vote yes or, okay. So we have to specify that so that the comparison would be based on the one we are highlighting, okay? So we select, specify success value. So whatever we are highlighting is the success value. The value we typed there was what? Yes. So we just type yes. All right. Then we say what? Okay. Can I click OK? Okay, okay. Then remember, we also specify that we must also give ourselves the confidence level so that it can tell us what it can compute, or the type 1 error rate, the one that we use as a benchmark, right? Okay, so that is on the test option. So I've seen the test option after the choose test, then the test option, it says specify your significant what level. So the significant level is 0.05. So automatically it's also specify 95% as the confidence interval. Okay, so this side is good. So in case you decide, no, for this particular test, I want to perform it as a much lower error rate, you can change that here. Okay. All right. So once we are done, we are good to go. We can just hit the run button. All right.
The exclude cases list, what are that?
The
What you run.
oh, I can't see that. Let me see from your side. Yeah, there are always so many options, but pick the ones that are yes. So this is probably if there are some cases that you want to remove, then you have to specify them. But those options are we are not using them. Okay, so can we all see the results I've shown? Okay, so how do we? So we see that it is testing. It gives you the hypothesis summary, and then SPSS is even smart. It says what? Decision is what? Reject the null hypothesis. What was the null hypothesis? That the proportion is what? 0.6. Okay. So if we are more extreme, then we do what? We if the proportion is not 0.6, but whatever we have observed, which is 0.6, is more than the what? Computed it, we got what? 0.66. It was higher than, slightly higher than 0.6, but we're not sure whether it's just by random chance. Okay, so we perform a test, and the test is telling us, because based on the p-value, that we have to reject the null hypothesis, because the p-value is much smaller than what? The p-value is much smaller than the error that we specified, right? Okay, so if it is much, it means that if whatever we observe, we can compare it with what the cutoff was. That was 0.6. So if the value
Point because of after it, I got my mistake. What would I do from here? I could have that.
Yours is what? Mistake and I have business. Okay, let's see what I sample. So let's go, let's see your data.
You are Nobel man.
Okay, so you see the way you type the yes, and you see the way you type the no. Let's go and see when you analyze one sample. Okay. Let's see the test options. You type capital yes, so it does not see this.
You take capital.
No, so you have to make sure that you use the, when you type the yes, it must be consistent.
Hello.
It's more YES.
Online. Yeah, yeah.
Online is.
Hello. I couldn't do
Yes.
the practice.
You couldn't do it.
Yes.
Oh. It's because you are using your machine and then your machine is also viewing, right?
You know, when you enter the yes or no on first on the variable data.
Yeah. Can you see the yes and the no's?
Yeah, that's the data view. But the
Yeah,
variable
data view.
data and the variable view, what did you do
Oh.
at the variable view?
Oh, the variable view. Okay. So I'm showing that. Can you do that quickly? You just
Okay.
type the support and then select string as the type.
Uh,
And then in counts, you also type
support,
count.
the type should be string rather, not
Yeah, the type for
numerical.
support should be string.
Okay.
And then the count part will be numeric.
Okay. Count.
Are you done?
Yes, please.
Okay, now I'm switching to the data view. So then the data view, you will see
Mhm.
that the two variables that you specify, they will show up here. So you have a yes and a no, and then you can count the yeses and you can count the no's. Do you have that typed?
It's typed, but the yes or no didn't appear. Okay, then I didn't do the labeling.
So don't label,
Okay.
just type it, just type them yourself.
Okay,
And the support,
Okay.
just type yes and then
Okay.
type the no. And then put the count there. So just type them yourself.
Okay. 495.
495, then the no is 255.
Okay, I got that.
Okay, so then we can go ahead and analyze.
Okay.
So in your case, you have to first do the weighting. So you go to data and then you go to weight cases at the end.
Weight cases, okay.
Okay. Move the count variable into that frequency variable.
Okay, done.
Have you done that? Okay, and then you say okay.
Okay.
Then now we can do the analysis. So you now go to analyze. Non-parametric.
Non-parametric, okay. One sample.
Then one sample. Okay. So some option will come, just select, just say, take the first option.
Okay,
and then it will bring you to
one data.
Scan data, yes, scan the data.
In the next 10 minutes.
Have you scanned that?
Yeah, so it's give me
Then now you choose the custom analysis.
yeah, custom analysis. Okay.
Okay, then you move to the field part.
Okay.
The field part, make sure that the support is on the test field. Is it moved to the test field?
Yes, please.
Okay, then we move to the settings.
Settings. Okay.
In the settings, choose the customize test option and select the compare observe binary.
Compare observe binary. Okay, that's the
Probability.
first.
Okay. Have you selected that?
Yes, please.
Then we are going to use the option. Click on the option.
Option, that's test option.
Yes.
Okay. So significant level 0.05.
No, not there.
Oh,
Where you selected the previous one, go to the. So let me move back on the choose test. On the choose test, you selected customize test, and
okay.
then the compare, just below the compare observe binary, you will see options there.
Options. Okay.
Yeah, select that options.
Yes, I've done that.
And then specify the hypothesized probability is 0.6.
Okay, I should write it down there.
Yeah, just use the arrow to keep to move them by decimal places. So if you move the top arrow by 8 or the down arrow by 8, the numbers will increase and decrease.
Okay, from 5 to
And
5.1.
to change it to 0.6. So keep
0.6.
increasing it to
Okay.
0.6. Are you at 0.6?
Yes, please.
Okay, then now when you go below it, you will see specify success value.
Yes.
Select that one and type the yes, which is the one we want to calculate the probabilities on.
I should type yes or
Yeah, type yes. The yes that you type in those options
okay.
when you were entering the data, type
Okay.
that in that. So the way you type it is case sensitive, so you must type it the same way as you have typed there.
Okay.
Okay. Have you done that?
Yes, please.
And then you say yes. Then you can run your analysis.
I'll say okay, then run.
Run, yes. So when you run, you will see something like this.
Non-parametric tests, then the hypothesis test summary.
Okay. So you can see the options, right?
Yes.
And reject the null hypothesis.
Yes, I see that.
Oh, okay. All right.
Thank you.
Okay, so it's time for lunch. So let's go for lunch, and when we are back, we'll continue. So you see that I did not highlight on the expected or the hypothesized so much, but that is what compute that. What is hypothesized based on the population, and then what we observe, and then it's looking at that difference. Okay, so that is all that is giving us the key values that we have. So it takes all that. So if you look at this one here, yeah, you see that they are not exactly the same, right? So this is
Alright, you are not eating. Please don't food, okay? Continue. If your food is ready, so let's eat and then come back. Let's go and eat, get energy, and then we'll do more exciting things. Oh, you didn't read it. Oh, let's see. Let's do it right. Come on. Mostly like that's why it's already tested. Yes, because it's 0.00, specify that we are dealing 5%. Note that it's less than 0.0. So that's the validate. Yes. Yes. So if it's yes, then it's 60%, right? So then the no will be the but those values are used here. So I did if you look at my slides, I've actually done that, but because of the time, you can actually do it by so the slides is there with the hand calculation so that you understand what is happening. Okay, so the calculation is this one here. Okay, so you see this Z statistics, the value was 3.35. We got that value in SPSS calculated it for us. So we would have calculated this to use it for the decision making. So when you are doing the inference, they likely would go about it. But another way of doing this is the p-value.
because the software is doing the p-value, that is why I'm explaining the p-value part for you. So the p-value and whatever is there. So it is this value here, 3.235, that is being compared with the 0.05. No, so this one is what is used to compute the p-value. And so you see it's in the, let's it's the value there is what? 3. So see what is that is doing. This is what we have observed, which is the 0.66.
Yeah.
This is what
The hypothesis.
we hypothesize, okay,
0.6.
and then we divide that by the variability that we said we are not. Once we because we said that data is following binomial distribution, so the variability is this one. Okay, so it computes this and gives us this value. Okay, so this value is now something like this. If I have like this thing. Let's say if the value is the value that the person hypothesized maybe is 0.6. Okay, and then the one that we have computed is 0.666. Okay. The p-value is calculating the area here, the area far away to the left of what you have observed. So the probability that you have observed something more extreme. Okay. If this bar here moves closer here, right? Assuming that this bar was very closer here, what has happened? It means that this value is far away from what? This value. So if this value is far away from this value, then the area here will be what? Small. Right? Because if I compute the area here, then that value will be very small. But because, so whatever I calculate here is the p-value, which is measuring the area to the left. So if this area is big, then it means that you are closer to this. That means that the person, what the person has said is true, it's true, right? But if the value is, this value is far away, then it means that, and you can know that by seeing that this area is what? Very small. So whenever this value is very small, it means that the person is what? Far away from. That means that what we have seen is far away from what the person has claimed. So if it's far away from what the person has claimed, then the person's claim is not true. The alternative is true. I don't know whether this, I didn't want to go here because I don't want to confuse people. Yeah, explain it better. Okay. Yeah, so the space to the right here is what we call the p-value. So if the p-value, so we agree that so when we, so it's more clear, it's a bit different from this, but we are saying that this area here that we are allowing is 0.5. That's the one that we have allowed. Okay. So if we allow the 0.05, then any area on that right means that you are smaller than the 0.5. Okay. So that means that, so, and that is the criteria that I'm using here. So this one here that I have, okay, I have one which is the 0.05, which gives me like 2.33. When I use the 0.05 to calculate it, I have something here. Okay, but what I have observed is 3.2, which is where? Here. So we call, whenever I use the 5% to do this, then the area to the right of that percent is called the rejection region.
No. Let them come and eat back. Please come and come back. Please come and eat. Please just take your food. Come and take your food. Why? Please come and take your food. Right. Time. Right. We will come back. Okay.
No, we have to talk. Research. I'm yet to get my the final
response of that school. But I want to review and see if we did some analysis. I want to review and see if it's possible for better grade and then supervisor, because oh, I had a bit of a challenge, so we delayed, so I should have graduated. So I did MPH as 2019.
MPH.
Yes.
Oh, okay.
I'm more into the social science, so social media. But my research, I didn't do the quantitative. I did a bit of quantitative.
So then what you said is that the masters or
Please, have you been said? Has everybody been said?